Whoever is
Yeah.
talking.
Can you hear me okay?
Yes, fine.
And can you see my screen as well?
Yes, we can see your screen.
Yeah, that's great. Hello, I'm John. Today I'm going to present a paper with Dimitar on ontology graph embeddings and ILP for financial forecasting. So just a bit of background on where we get the data. So there is, in United States, there is the Security Exchange Commission, where they it's an independent agency where they provide on how the companies needs to report their results, as well as what they need to, if some of the directors or employees do some trading, they need to inform the SEC with this structured reports. So what we've built is a essentially it's something that consumes all the SEC reports, and there are different forms in the SEC one. There is something called Form 10, which deals with the company's financial structure. This particular research is looking at the Form 456, which deals with the employees or directors' share purchases and sales. And it turns out when we look at these reports, this particular one is a very structured report where we get the company personnel with how many shares they bought, and as well as the relationship with the company. So from these reports, which is just XML files, we generated our own ontology, our own knowledge graph to be able to drive this the information that the experiment that I'm going to describe in a minute. So the ontology is probably is everybody knows, but it's basically a triplet, and essentially it's a graph structure, and some terminology. Individuals are called classes numerically, and then we have links that links to the other entities in the graph. So ILP learners using the description logic exists. For our case, we did a little bit different. So in order to apply any machine learning to existing machine learning algorithm to ontologies, so first we need to convert to Euclidean space. So in the graph representation learning is so we use an existing algorithm called NOTWEC, which essentially translates the ontology graph to a vector space, so that a regular machine learning algorithm can be applied. The way the NOTWEC works is uses random walks and gradient descents to generate the vector representation, so-called embeddings of nodes of a graph in this vector space, and then the distance that reflects the weighted neighbor proximity and the similar topology put together on the NOTWEC embedding. So essentially, and then so let me go to the clustering a little bit. Once we converted our ontology to the vector space, and then we can, using the NOTWEC embeddings, we can apply an existing k-means algorithm to label our data, and essentially we use that in our ILP learner as a background information. So just to go through the experiments very quickly on what we've done. So we get the ontology data, which is an XML. We load on an ontology engine. We run some queries to build the relationship between employees and the companies. And then once we load that, we build our graph, which consists of the employee and the companies they work for. And it turns out when on the companies that needs to file to SEC, it turns out that some employees are being shared by multiple companies. So that gives us a nice relationship between an employee or director being on several companies. And then we feed this data, we split the data on the training and test set, and then which is the main forecasting task of the experiment, is the co-integration. So for those who doesn't know, co-integration is the metric to say if two companies time series move together in either the same direction or the opposite direction, but the point is if one of them goes up, the other one goes up, or if the one of them goes up, the other one goes down, so that they follow the same co-integration pattern. And then there's a trading strategy called pair trading. If a company is co-integrated, then you can make a profit out of those. Obviously, finding those co-integrated companies is a very difficult task. We had a sample of 1,000 companies, and taking the co-integration of all the combination of two of the companies is in the hundreds of thousands, and it's a very complicated task. So what we have done in this experiment is get the background information, find what people shares with what companies, get the not to work with the what cluster they belong to, and finally put that all background information. And
so there's 2 minutes left.
Okay, generate that on the Progol data, which I'm now going to pass on Dimitar to talk about the results quickly.
Okay, so essentially
Dimitar,
we have,
you'll have to be super quick, I think.
Yeah, I'm very quick. So essentially we have data. We're trying to basically learn a filter to get rid of some spurious pairs of companies, so we don't have to calculate the co-integration coefficient, which is a standard test, but it takes time. And for that, we use as background knowledge the cluster labels that we learned from the embeddings of our nodes. And we also have predicates that tell us whether a certain pair of companies are connected with each other, and what is the minimum number of connections to a person or to a company, and where a person is connected to a company or a company is connected to a person. Next slide. We have a bunch of rules, and if John presses enter a few times now, you'll see that there are rules of different type. They refer both to the cluster labels, which in some cases says the two companies should be from the same cluster.
Dimitar, I'm sorry to interrupt, but we're really out of time.
Can I just show my last slide?
Yes, please. Yes.
Okay.
Yes, go on.
So the very last slide says that we have learned, as a result, the set of rules, the last slide, which led through all the positive, all the genuine pairs of co-integrated companies, which we can test later, but it gets rid of half of the pairs that are not co-integrated, so it saves us half of the hard work because most companies are not co-integrated, and therefore it's a useful filter for this purpose, and we can save on computation quite a lot, which means that you can trade on a smaller computer and with more frequent updates of your co-integration tests. Thank you very much.
Great. Thank you. Sorry for the rush, but I think
we all want to see Gary's talk, so yeah.